Hello everyone, this is Samuel Akinwande and I will be providing a brief overview of the code required for the numerical analysis problem of the second project of ENGI 1331 at the University of Houston. Now, due to the time constraints of the video, I cannot go in depth into the solution, so I would have to try to summarize the methods. So here we go. For the first problem, you're required to essentially solve a linear algebra problem. You should find the upper triangular form of a given matrix and use that form to find the solution to that matrix. And our approach to that problem was to create a code using for loops that essentially evaluates first the value of that the value at that point and uses algebra to convert that value to a zero. And that's the code right here. Now I can't walk you through the code, but you can the code essentially does that. It uses based on the size of the input and everything, uses a for loop to essentially get it to be a zero. Next we got that we took that output from the first function. That the first function is called the uptree function. And we took the output from the uptree function and input it into another function called the backsub function. Now the backsub function uses a backward substitution, which is essentially solving a system of equations. Imagine doing it by hand, but a computer essentially does this because it's a lot faster when a computer does it. So we used again another set of for loops to essentially get the computer to solve that. Now, one thing that I would like to point out is this specific line here, because if you imagine, if you will, a square matrix that there's a diagonal from the top left corner to the bottom right corner, and every value beneath that diagonal is a zero. So if you can see it, you can see that the very the final value, let's use this as an example. So this is an n by n matrix, and this is the upper triangular form right here. Here's the diagonal line. The values beneath the diagonal line, here, here, and here, are zero. So you can see that this has no this variable, this whatever this is, has no competitor. So it has to be whatever this variable is, has to be 5 divided by 7. So we essentially, because that's the only way to find that value, we can't solve for it. It has its own specific definition. So we do that right here. And using that, since we already know what that one variable is, we can then plug that into the other variables. Now remember that each column is a different variable, so you can use that that knowledge to find the other ones using this loop, these set of loops. And we have a sort of data validation step to ensure that if one of the values is already a zero, because you don't want to divide by zero, so you check that if one of the values to be divided with is a zero, you just output an error. And we have a bunch of outputs well, not a plot, but here we have a couple of F and F statement, and we have a formatted output for the solutions of the matrix or of the system of equations. And that's we have some data controls to restart the function if the user wants. If not, we can just end the function. And for the second problem, a numerical analysis problem, which is a bit more complicated, but you essentially have a polynomial that you want to solve, and the polynomial can vary in size, so you have to account for that, which kind of eliminates the choice of using a function handle or a function. But we can we have a little hack to account for that. But what the problem wants is for you to just solve a system of equations, solve a polynomial using the bisection method. The bisection method essentially tries to find a zero between 2 points, and just keeps decreasing the interval of those points until you get to a small enough interval that the value of the function, the difference between that the difference between the actual root and the interval is less than a certain error. So what we do here is we have using the bisect root function, we have essentially have a counter and a bunch of for loops based on the size of the function, just keeps running the function. Now, if you remember earlier, I mentioned that we can't have we can't use a regular function because the size of the user input is bound to change. So instead, we use a for loop that essentially checks for for the midpoint, for the upper bound, and for the lower bound, and like compares it. That like technically counts for the varying size of the potential user input. And now here we have like a essentially check that like the function is still like crossing the 0 point. So if it's not, well, like we change the interval like just a slight little bit and rerun the function until check, which is our error, is less than the user inputted error. Once we get to that point, we have a certain number of iterations, and we have the estimation of that root. Note that like the estimation is not the actual root; it's just like an estimation less than a certain error range. Now the problem also wants you to like plot the amount of error you have per iteration, which is actually a bit complicated. Like it's not actually that complicated. Just like replicate your first function, but this time actually don't overwrite the value of your error. Just like store it in a variable, which is essentially what we're doing here. Like you can condense this into one function if you want. Like here, you can condense this into like the first function, but the problem requires you to like have two functions, which is why we have two functions here. But you can do it in one function, and once you get like the outputs of that, which is bisect root 2, you can then plot it as like the function once, and the function wants you to like plot a fit to the data, which is like the from like by experimentation we found that like the data, like the perfect plot or the perfect fit to our plot is actually like an exponential fit, which if you look at the equation for the error actually makes sense. So just like plot an exponential fit to the values, and you should get like you should get the right fit. And it also wants you to like plot the difference in the estimated root versus the actual root per iteration, which is essentially like the first plot, which is the plot of the maximum error. But like you make some slight little changes which you account for down here, but overall it's basically the same code. It's just like replicate it for like and make some more changes to it. Now after you get the plot, you can display to like you actually have to like explain why your selected fit works for the code, and we do that by like explaining that like based on the equation here, you can see that like let's see here, this equation, you can see that like the error actually decreases exponentially based on the number of iterations, which is n. N is the number of iterations, so it decreases exponentially. And actually the professor let out like you recall the question, because this equation is actually kind of wrong. It's 2 to the n, because this is a geometric relation, but like the correct equation is 2 to the n. So it's an exponential relationship, and the plot actually shows that. Now I'm gonna test the code right now, and testing the first one, and we're gonna use the test cases provided by the problem just to ensure that like we're getting the right answers. Because like if I find test cases, then like you wouldn't know if I'm getting the right answers or not. So they use this matrix like 1 0 3 4, and they use 1 0 3 4 and 1 minute here. 1 2 1 3, and we have 1 2 1 3, and it's the last one, 0 6 1 2, 0 6 1 2, boom. And we have our outputs. Now let's compare the outputs to the like, I take no because like there's the option to restart the code, but we don't want to do that. We just want to like see that the function works. And if you look at our upper triangular form, if you look at these numbers and compare it to these numbers, you can see that like they're the same thing. And the solution to the problem, which is this, it's kind of sloppy output. Like we made it a bit cleaner, but it's essentially the same thing, which kind of proves that like our code runs. And for the second problem, for the numerical analysis problem, we have like if we run that, we have this input for it. We have the upper bound is 1 and the lower bound is -1. We can do that, and -1, do that. The vector values, okay, give me 1 minute. So the vector of values is actually 3 4 26 and 1. We have 3 4 26 and 1, and the maximum error is 0.001 as specified by the problem. And you can see that like we have a bunch of like we have the plot. I'm not gonna restart the program, so that's a no. But you can see like we have our fit, like we have our specified fit, and we have our second plot. Like they display like an x, like this looks exactly like the exponential function, but like just flip it. So this displays the appropriate relationship, and it shows that like the code works, and we have the right answer. Now the professor actually provided his answer, which let's output the root here. Root no root, which is, and let's also provide the maximum error and the number of iterations, and compare it to the professor's. We have like 11 iterations. The professor had 11. The maximum error was 9.76 times 10 to the negative 4. We have 9.7656, so it's even a bit more accurate, times 10 to the negative 4. And our root is the professor got 0. Negative 0.00400, but he explained that like using Wolfram Alpha, you actually get like negative 0.039, and our code got negative 0.039. So code works, but the limitations of the code is that like one, if you have a function like a matrix that doesn't have a solution, the code actually just like gets an error. So like it doesn't solve it. Like it doesn't try any other approaches. It just sort of like stops the code. And I think that's like our major limitation right now. But like for the specific problem that it was made for, the code runs just fine. And this can be applied. I think like I'm definitely going to save this for when I actually take linear algebra or like numerical analysis. But like I can't actually see many applications outside of this class or those classes. But like you can definitely use it for like your future classes. And I think the project definitely like achieved its goal of, I guess, introducing freshmen to like these topics that we'll be going over in our senior or like junior classes. And that's our code. Thank you very much. Stop.